Hello, my dear students. Welcome to IKSR chemistry classes. In this video, we will discuss Tanabe Sugano diagrams, that is TS diagrams, and their use in the calculation of Racah parameter and crystal field splitting parameter. Let us first of all introduce the topic. Like Orgel diagrams, the Tanabe Sugano diagrams are also correlation diagrams, which describe the correlation between various electronic terms of free metal ion and the electronic terms of metal ion in the complex compounds. It is obvious that Tanabe Sugano diagrams are correlation diagrams which describe the correlation between various electronic terms of free metal ion and the electronic terms of metal ion in the complex compounds, as in the case of Orgel diagrams. However, TS diagrams differ from Orgel diagrams in the following aspects. In the TS diagrams, that is Tanabe Sugano diagrams, the ground state is always taken as abscissa, that is horizontal axis, that is x-axis, and it provides the constant reference point. The other energy states are plotted with reference to the ground state. It means during plotting TS diagrams, the ground state is always taken as abscissa or horizontal axis or x-axis, and the energies of other states are plotted with respect to the ground state. The energy of ground state is constant. It is on the x-axis, and the energy of other states is expressed with respect to the ground state. And the low spin terms, that is the terms having a spin multiplicity lower than the ground state, are also included in TS diagrams, while in Orgel diagrams only those states are included which have the same highest spin multiplicity. But in TS diagrams, the states with a spin multiplicity lower than the ground state are also included. In order to make the TS diagrams more general, for different metal ions with the same electronic configuration, and to allow for different ligands, in order to make TS diagrams more general, for different metal ions with the same electronic configuration, and to allow it for different ligands, both of which affect DQ and B. Both these metal ion as well as the ligands affect DQ and B, and in order to make TS diagrams more general for different metal ions and different ligands, the graph is plotted in units of E by B and dq by B. That is, E by B is plotted against dq by B. Let us recall, in Orgel diagrams, the energy is plotted against crystal field strength. But in TS diagram, E by B is plotted against dq by B. TS diagram for D2 and D7 octahedral complexes. The simplified TS diagram for D2 octahedral complexes is given below. The TS diagrams are quite complicated, but for beginners, simplified TS diagram is more useful and it can be understood easily than the complicated TS diagrams. Here in the sidewise figure, simplified TS diagram for D2 octahedral complexes has been given. E by B, energy divided by Racah parameter B, is plotted against dq by B, crystal field splitting parameter divided by B. dq by B is taken on the x-axis while E by B is taken on the y-axis. It is origin 0 point. dq by B increases in this direction 1, 2, 3, 4, 5 and E by B increases in the upward direction 10, 20, 30, 40, 50 and 60. The ground state for D2 metal ion is triplet F and the excited state is triplet P. These two states have the same spin multiplicity. These are the spectroscopic states having the same highest spin multiplicity for transition metal ion with D2 electronic configuration. When D2 transition metal ion forms an octahedral complex, triplet F state splits up into three states: triplet T1GF, triplet T2G and triplet A2G. Here triplet T1G has the lowest energy. It is the ground state and hence its energy is taken constant and it is taken on the abscissa on horizontal axis, that is x-axis. The energy of triplet T1G is taken as abscissa, x-axis or horizontal axis. Its energy does not increase with increase in the value of dq by B. The excited state triplet P does not split up in octahedral crystal field. However, it transforms into triplet T1GP. Here, these two terms, triplet A2G and triplet T1G, have different symmetries and hence they can cross each other. There is no violation of non-crossing rule. This Tanabe Sugano diagram has been plotted for D2 octahedral complexes. It is also applicable to D7 octahedral complexes, D3 tetrahedral complexes and D8 tetrahedral complexes, as in the case of Orgel diagrams. However, for D3 and D7, the spin multiplicity is 4. But in the case of D2 and D8, in the case of D2 and D8 transition metal ions, the spin multiplicity is 3, triplet F, triplet P. But in the case of D3 and D7, it will be quartet F and quartet P. At the same time, for tetrahedral complexes, the suffix G is omitted because tetrahedral complexes don't have center of symmetry. This is the TS diagram for various complexes D2 and D7 octahedral complexes and D3 and D8 tetrahedral complexes. Such complexes should exhibit three absorption bands in the UV visible spectrum due to these tritions: the first trition, the second trition, and the third trition. Calculation of D, Q, and B from TS diagrams. Vanadium H2O holds 6 triple plus ion having electronic configuration 3d2 in the aqueous medium exhibits two absorption bands at 17,200 cm inverse and 25,600 cm inverse. This complex ion has 3d2 electronic configuration of the central metal ion. It is an octahedral complex and it exhibits two absorption bands in the aqueous solution. These absorption bands may be assigned to following transitions: triplet T1GF to triplet T2G and triplet T1GF to triplet T1GP as shown in the sidewise figure. This is the diagram for, this is TS diagram for D2 octahedral complexes. These two absorption bands have been assigned to these transitions: triplet T1GF to triplet T2G and triplet T1GF to triplet T1GP. This one. The ratio of 25,600 cm inverse and 17,200 cm inverse is 1.5. The ratio of these wave numbers is 1.5. If we draw a vertical line at dq by b equal to 2.8, this vertical line, we get E1 by B, the first transition, E1 by B equals to 26 and E2 by B is equal to 39. If we draw a vertical line at 2.8 at dq by b equal to 2.8, a vertical line is drawn, then we get the value of E1 by b equals to 26, E2 by b equals to 39 and E3, the third transition, by b equals to 55. E1 by b, E2 by b and E3 by b. The ratio of E2 by b is equal to the ratio of these two terms. This is E2, this is E1, is 1.5. In this case also, the ratio of 39 and 26 is equal to 1.5. E2 by b divided by E1 by b, b will be cancelled out. It will be equal to E2 by E1. E2 has been given. The energy required for second transition is 25,600 cm inverse and the energy required for first transition is 17,200 cm inverse. Their ratio comes to be 1.5 as we have discussed earlier. This relationship can be obtained at dq by b equals to 2.8. If we draw a vertical line at dq by b equals to 2.8, E2 by b comes to be 39 as we have said, and E1 by b comes to be 26, and their ratio is 1.5 as obtained in this case. Now E1 by b is equal to 26 and E1 is equal to 17,200 centimeter inverse, and therefore B will be equal to 17,200 centimeter inverse divided by 26, and it comes to be 661.5 centimeter inverse. This is inter-electronic repulsion parameter in vanadium triple plus ion in VH2O whole 6 triple plus ion, and hence it is actually B dash, not B. dq by B is 2.8. At this point, this relationship comes to be, and therefore dq will be equal to 2.8 multiplied by B, and the value of B has been calculated already. 2.8 multiplied by 661.5 centimeter inverse, and it is 1852 centimeter inverse. This is the inter-electronic repulsion parameter, and this is crystal field splitting parameter which have been calculated using TS diagrams. And now the term for Nephelauxetic ratio B dash by B, and it is equal to 651.5 centimeter inverse B dash, and B is equal to 861 centimeter inverse. This value has been given in the table in previous videos, and the value of beta, that is Nephelauxetic parameter or Nephelauxetic ratio, is equal to 0.76. Thus we have calculated Racah parameter, crystal field splitting parameter, and Nephelauxetic parameter with the help of TS diagram. Now the time for self-assessment. Find out the wave number of expected third absorption band of VH2O whole 6 triple plus ion. It actually exhibits two absorption bands. In the UV visible spectrum, we have to find out the wave number of expected third absorption band. We have already seen that E3 by B is equal to 55. It has been obtained by drawing a vertical line at dq by B 2.8, and therefore E3 will be equal to 55B. The value of B has been calculated, 55 multiplied by 661.5 centimeter inverse, and the result is 36,382 centimeter inverse. This is the wave number of expected third absorption band in the UV visible spectrum of VH2O whole 6 triple plus ion. E3 transition, that is the third transition, involves the excitation of both the electrons simultaneously, and hence it requires very high energy, and it is generally not observed in the normal UV visible region. This wave number does not fall in normal UV visible region because this transition requires very large amount of energy, because both the electrons are excited simultaneously, and hence the third absorption band is generally not obtained in the normal UV visible region. This transition involves the excitation of both the electrons from ground state to excited state. It requires large amount of energy, and the wavelength of wave number, not wavelength, wave number of absorbed radiation is very high, which does not fall in the normal UV visible region, and hence the third expected absorption band is not observed. TS diagram for D3 and D8 octahedral complexes. The simplified TS diagram, as we have already said that the TS diagrams are quite complicated, and for beginners the simplified TS diagrams are sufficient. The simplified TS diagram for D8 octahedral complexes is given in the sidewise figure. For D8 transition metal ion, the ground state is again triplet F and excited state is triplet P. Here also E by B is plotted against dQ by B. When D8 transition metal ion forms octahedral complex, triplet F state splits up into three states: triplet A2G, triplet T2G, and triplet T1GF. The triplet P state does not split, however, it transforms into triplet T1GP. Here, these two states, triplet T1GP and triplet T1GF, have the same symmetries and they repel each other in accordance with non-crossing rule, so that they may not cross each other, and their bending away from each other increases with increase in the strength of ligand field. It is also applicable. This TS diagram has been plotted for D8 octahedral complexes, but it is also applicable to D3 octahedral complexes, D2 tetrahedral complexes, and D7 tetrahedral complexes. However, in the case of D3 and D7, the spin multiplicity is 4. For D2 and D8, the spin multiplicity is 3. But for D3 and D7, the spin multiplicity is 4, and at the same time, for tetrahedral complexes, the suffix G is omitted because tetrahedral complexes have no center of symmetry. Calculation of DQ and B from TS diagrams. NiH2O whole 6 2 plus ion in the aqueous medium exhibits 3 absorption bands at 8,700 centimeter inverse, 14,500 centimeter inverse, and 25,300 centimeter inverse. These absorption bands may be assigned to the following transitions: all transitions arising from triplet A2G, which is the ground state, which is the constant reference point, which is taken on the x-axis or abscissa, horizontal axis. Triplet A2G to triplet T2G, triplet A2G to triplet T1GF, and triplet A2G to triplet T1GP. This is the TS diagram for D8 octahedral complex. This is D8 octahedral complex, and 3 transitions are expected: triplet A2G to triplet T2G, this one, triplet A2G to triplet T1GF, this one, and the third one, triplet A2G to triplet T1GP. 3 absorption bands are obtained in the UV visible spectrum of this D8 octahedral complex arising due to these transitions. The ratio of E3, 25,300 centimeter inverse, and 14,500 centimeter inverse comes to be 1.72. The ratio of these two terms E3 by E2 is equal to 1.72. And this ratio fits if we draw a vertical line at dq by b equals to 1. If we draw a vertical line at dq by b equals to 1, we get E3, this is third transition, E3 by b equals to 28. And E2 by b, this is the first transition, this is the second transition, and this is the third transition. E3 by b equals to 28 and E2 by b equals to 16.3. And their ratio comes to be 1.72. Here also the ratio of 25,300 and 14,500 is 1.72. On the basis of these data, the crystal field parameters can be calculated as follows: E3 by B divided by E2 by B, B will be cancelled out and it will be E3 by E2, 25,300 centimeter inverse, third transition, and 14,700 centimeter inverse, and this ratio comes to be 1.72 as we have said earlier. This relationship can be obtained at dq by b equals to 1 if we draw a vertical line at dq by b equals to 1. E3 by b comes to be 28 as given in the earlier slide, and E2 by b comes to be 16.3, and their ratio is 1.72. E3 by b is equal to 28. Therefore, B will be equal to E3 by 28, 25,300 centimeter inverse, and it is 903.5 centimeter inverse. It is actually B dash, inter-electronic repulsion parameter of metal line in the complex compound. dqib, vertical line has been drawn at dqib equals to 1.0, and therefore dq will be 1 multiplied by b, that is 903.5 centimeter inverse, and it is 903.5 centimeter inverse. This is Racah parameter, this is crystal field splitting parameter, and now Nephelauxetic parameter b dash by b, 903.5 centimeter inverse divided by 1030 centimeter inverse. This value has been given in the table in the previous videos. This is inter-electronic repulsion parameter in free Ni2 plus ion, and this is inter-electronic repulsion parameter of Ni2 plus ion in NiH2O whole 6 double plus ion, and this ratio comes to be 0.88. Thus, we can calculate the Racah parameter, crystal field splitting parameter, and Nephelauxetic parameter with the help of TS diagrams. Thank you for watching the video with concentration. Please like and share it. If you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.